Hello everyone, welcome to this lecture number 11 of NPTEL lecture on charging infrastructure. In this particular lecture, we will further go in detail about a single phase boost PSC converter. If we see in our previous discussions, in our previous lecture, we have seen how this converter works, where we have full bridge diode rectifier followed by the boost converter, and here we have this particular full bridge diode rectifier will actually give VD value, which is actually nothing but modulus of Vs of t, you can say, and which indicates somewhere around the variation will be the modulus of sine omega t, and it has the voltage which is the with positive polarity. So, and then again we have understood that the switches S1 and S2 need to be switched at a high frequency as that of the supply or AC input. So we have also seen that our F switching of the devices has to be greater than Fs, such that the rectified DC which is coming across the A and B applied for that switching period, it will be like a constant voltage. Then we have derived the duty ratio, that means the fraction of the time of the switching period when the switch S1 need to be on. We have seen that since the input to this boost converter is varying in a fashion like this, so the duty ratio, this is the VD value, so the duty ratio also have to be varied in such a manner that the constant V0 voltage is achieved at across the load resistance. So if we assume that our output is a constant V0, then our duty ratio varies from between 1 to going near to 0, then again come back to the same value 1, and then again from here to here again it goes near to 0 and again comes to 1, and this period is nothing but 1 minus Vs peak divided by V0. So, and here we have also seen, because of this particular constant, we have seen that since the duty ratio need to be varied between 0 and 1, that indicates that the V0 has to be greater than Vs peak. That means always you will get the output voltage greater than the peak value of the input sine wave. So where if we assume the 230 volt as input, then our peak goes to 325 volt, that's when the V0 has to be greater than 325 volt. Generally the common practice is to take V0 is equals to 400 volt. Now this is the understanding we got while deriving this duty ratio, the time during which this S1 is on within that switching period, while the remaining of the switching period is the S2 which will be on. So we can say that for S2 switch, the duty is nothing but 1 minus, or the duty of, let's say, S2 switch is nothing but 1 minus d of t, which is nothing but 1 minus of this, which is nothing but modulus Vs peak sine omega t by V0, while for S1 the duty ratio will remain be the same as d of t. So these are the understanding we got up till now, things related to the duty ratio. Then we move ahead and started seeing the different components, like started sizing the different components, because that is also important once you are going to design this kind of AC to DC converter, which is nothing but a boost power factor correction converter. So when you are designing that, you need to size your inductance value, you have to appropriately size your capacitance value, your S1 switch and S2 switch, the voltage and current rating need to be defined, and similarly our D1, D2, D3, D4 ratings need to also be defined, such that one can go and select the appropriate components. So, in that process we have derived that what will be the value of inductance which is needed. We have come across this expression, which depends upon the output voltage and the maximum ripple current or allowable ripple current. Generally it is taking 10% of Is peak, where Is peak is nothing but the current which is been drawn from the source. And generally, since this converter is operated in a such a manner that you are drawing the unity power factor current, so we can just write Is peak times or Is peak sin omega t, where the phase difference between the AC voltage and the current drawn from that voltage source is in the same phase. So we will take that allowable ripple current, generally it is 10% of the ISP, which we can easily calculate if you know whatever the power level of, I mean for what power level we need to design this converter. Based upon that, you can take, you already know the grid, a single phase grid voltage generally in our system. So using that we can easily evaluate our Is peak value, and we know this could be the maximum current which is there in the circuit, and accordingly we can define our allowable current ripple. Also, if you see, the inductance value depends upon the switching frequency of this S1 and S2. If this switching frequency goes up, then the value of this inductor required will go down for the same allowable ripple current. So this is the condition we got while when we derived this inductance value. Now let us see how we can size this capacitance value, another passive component. So one passive component we have defined. Now let us see how we can size the capacitance. For that, again, what will be the capacitance value needed to keep the output voltage within a certain allowable ripple. So let us try to again relook our converter, and here we have Is. Now let us define this Is value. Since we are assuming that the converter is operated in such a manner that the unity power factor current is drawn from the AC voltage source or from the single phase AC grid. So assumption is that here we are actually doing the sizing of C, or the capacitor which is present. So one assumption we have taken, assumption is that the converter is operated in such a manner that the unity power factor current is drawn from the grid. That implies my Is value is nothing but Is peak times sin omega t, and my Vs value is nothing but Vs peak times sin omega t. Both are in same phase, and the phase difference is 0 in between the Vs and Is. Now since we have assumed this particular condition, so we can calculate the power at the input, or we can see power at the input. Now this power at the input, if you do a simple mathematics, which is nothing but Vs peak sin omega t times Is peak sin omega t, because these are the thing, these are the basically your input, this is rectifier circuit, and this is your boost converter. So our P input, we can calculate the amount of power at the input or the power drawn from the input, you can take. So which is nothing but we can write this one Vs is peak sin square omega t. Since we have already assumed that this particular converter is operated in such a manner that the unity power factor current is on, so we can write the expression in this particular format. Now that particular thing will give you the relationship as Is peak 1 minus cos 2 omega t by 2. Now that implies we can write Is peak by 2 minus Vs peak Is peak cos 2 omega t by 2. That is nothing but your input power. And we can also see, if we see here, the current which is coming out of this half bridge is I converters, the some portion is going into the capacitor while the average value is coming through the load, and that we define that average value as IL, which is actually going through the load, and while the ripple portion of this, or the ripple which is present in the I converter, will be flowing through the capacitor. So we can also see one simple thing, that whatever the current which we are getting over here and the voltage which is here across at this point, we can write simply the power at the output of the half bridge. We can write that power at the output of half bridge let me define this power as PD. Now that is nothing but, we can write my I converter current, which is obviously varying with time, multiplied by value V naught, which is the voltage appearing across this particular point. Now if you look very carefully, this particular power is also varying with time. So we need to write P in with respect to time. This is varying with time. So similarly, this power which is going into the parallel combination of RL and C is also varying with time, where this I converter is actually varying with time. So we can write the PD value as this one. Now let us define this as equation number 1, this as equation number 2. Now if we look very carefully in this particular thing, what we have done is, we have calculated the power which has been drawn from the source and the power at this particular. And let us take one more assumption. Assume the losses in rectifier and boost converter is negligible. If this is another assumption we can take, then we can easily write that equation number 1 is equals to equation number 2. That means the power which is coming, which is drawn from this, is nothing but the power which is going into the branch or parallel branch of C and RL. So that we can write down that my P of in of t is nothing but PD of t. This sometimes also called as, by applying, I mean you can also say that by doing the power balance. Doing the power balance. So whatever the input coming is going actually into the output. So we can make sure we can write that P in of t is equals to PD of t. Now that will implies, if we try to write down our equation number 1 and equation number 2, we can write down I converter of t times V naught is nothing but Vs peak Is peak by 2 minus Vs peak Is peak by 2 cos 2 omega t. Let us see, yeah, this is the thing. So now if we see this particular expression, we can rearrange this, where we get is nothing but Vs peak Is peak by 2 V naught minus Vs peak Is peak cos 2 omega t by 2 V naught. Now if you look very carefully, this particular expression, this is the DC quantity. If you look very carefully, this particular I converter which is at this point is nothing but comprises of this DC quantity and the quantity which is varying at this second harmonics of this line frequency, because we have written omega. So we know omega is nothing but 2 pi fs, where fs is nothing but our 50 hertz if we are operating in India, and if it is in US it is 60 hertz. So if we see here, since this particular expression has 2 omega variation cos 2 omega t, so we have twice the frequency of what we have given in the input. So that's why it has the component, this particular current has the component which is having the second line harmonic frequency. So this is nothing but the second line harmonic current, where harmonics is in terms of input line frequency, that means 50 or 60 hertz. So this I converter comprises of the DC quantity and the second line harmonics current, which is also sometimes called as a double line harmonic component. So now if we see very carefully, this I converter which is there here is nothing but consists of a ripple and the DC quantity, while here since this I converter is going into the parallel branch of capacitance and resistance. So this the second harmonic component which is there will be flowing through this capacitor, while the DC component which is there will be going through the load. So we can write down that this I converter T comprises of IC, which is again varying with time, plus IL. So the DC component is going into the load RL, while the second harmonic or the double line frequency component is going through the capacitor bank. So let us calculate from that the ripple current which is going through this, and this particular part, if we see this particular component, this particular part will be flowing, will be going through the capacitor, will be through the, will be flowing through the capacitor, while this part will be flowing to the, or to the load RL. So the current which we see over here, I converter, as we have derived, comprises of this DC quantity and the second harmonic current, which is also sometimes called as a second line harmonic current. Now what is the second line harmonic current? Because line harmonic means it is second harmonic of the line frequency, which is nothing but a 50 hertz. Second harmonics of that, that means 100 hertz if we have 50 hertz, if it is 60 hertz it will be 120 hertz. So since this particular second line harmonic current will be flowing through this capacitor, which is responsible for generating this ripple on that capacitor voltage. So what we have is, we have a constant DC voltage, over that there is second line harmonic ripple which will be riding, and we will see how it looks like. So now we can write ICT nothing but minus of Vs peak Is peak cos 2 omega t by 2 V naught. And we can now, since this current is going through this capacitor, we can write out that the ripple generated due to the flow of ICT by the current IC, or the current going through the capacitor, is nothing but, we can write V naught ripple 1 by C IC of t dt, and that we can take down this particular thing as minus Vs peak Is peak divided by 2 V naught cos 2 omega t. Let us define this as equation number 3. And if you look very carefully, this, if you look very carefully in the previous slide, this particular thing is the DC quantity of the current, and that particular current will be flowing through this resistance RL. So we can write this particular value which is Vs peak Is peak divided by 2 V naught is nothing but equal to IL. So we can also write, Vs peak Is peak by 2 V naught is nothing but equal to IL, which is the average DC component of current in this I converter, or in present in this I converter. So now if we substitute this equation number 4, that will give you the V naught ripple is nothing but minus IL by C cos 2 omega t. Obviously here dt I missed in dt. Now this we can do the integration, we will complete the integration, so we will get the 2 omega outside, and then this will be nothing but sine 2 omega t. And so we can see that this particular thing which is shown over here, we can write this particular thing as V naught ripple peak nothing but IL by 2 omega c. Now if we look this particular expression that is given by 5, if we see this particular expression, this will have the second line harmonic ripple, and this ripple is riding over the average value of voltage, which is nothing but the V naught. So if we see our output voltage, so it will be like something like, so if assume this is my T and this is my Vs, which is nothing but Vs peak sine omega t. So I can write, I can define the V naught is nothing but having the DC quantity which is maintained at V naught, and over that you have the second line harmonic current, and depending upon the capacitance value, that amplitude of the ripple will be defined. If we see from equation number 5, since it is having the sine 2 omega t having the negative sign, that means it has the phase which is 180 degree as that of, so our actual voltage will also have this ripple, second line harmonic ripple. Now if you look very carefully, this is having the time period which is just t by 2, and this is actually t. And if we see, so this is nothing but the frequency is nothing but 100 hertz frequency. And if we try to define the this V naught ripple peak, so this is nothing but our V naught ripple peak. And if we try to see the ripple, it is this from this point to this point, from this peak to this peak, and as we already defined, the ripple is nothing but we can define as a delta V naught. Let us further take this equation number 6 and write down in terms of this V naught thing. So we can rearrange this particular thing and we can write IL divided by 2 omega V naught ripple peak, and 2 times ripple peak is nothing but delta V naught. So we can write IL by omega delta V naught, and we can then further write this IL in terms of load power and omega delta V naught times V naught, and that we can write C is nothing but PL by 2 pi Fs delta V naught times V naught. So this is what we understood, that we have the output voltage is comprises of the DC voltage over which there is the voltage ripple which is having a variation because of second line harmonic current, and that particular ripple is also varying with the second line harmonic frequency. So that's why this particular ripple will be defined in this manner. So, this capacitor, the capacitor C really sees the second line harmonic current and has ripple which is of second line harmonic frequency. And so this capacitance hold that DC voltage V naught, and along with that there is a ripple riding over that voltage or DC voltage, and that ripple has second line harmonic component. If the input is having 50 hertz, the ripple will have the 100 hertz component. If the input is having 60 hertz, the ripple in the capacitor voltage will be of 120 hertz. So, this is the very common phenomena which you will see in single phase AC to DC converter, where you see that the output capacitance has the voltage ripple which consists of a second line harmonic frequency. And this is why we see that the capacitor size in single phase AC to DC converter is one of the bottleneck which makes this single phase AC to DC converter very big in size. So, this capacitor is of large size because of second line harmonic frequency component. So, we need to size our capacitor in such a manner that this capacitance is able to withstand or is able to keep that ripple having second line harmonic component to be within the permissible limit. So, if we see in this particular expression of capacitance, this PL is the specification generally given, V naught is again the parameter which will derive from the specification. So, you can say it is a specification. Delta V naught is the allowable voltage ripple, which is again one of the specification, and this Fs is the line frequency, which is again one of the specification. So, all the things which is given here will be defined in the specification whenever the specification for this AC to DC power converter is being given to you for designing. So, using those specification, one can easily size or one can easily come to know that what will be the value of capacitance C. So, we have understood or we have seen what is the value of L which is present here, we have seen what will be the value of C. Now, let us try to see how one can define the rating of those switches, and then we will see how one can define the rating of these diodes. So, let us see for the switch ratings. How they are defined. Let us take for S1 switch. We know that this particular S1 switch, when the S2 turns on, this S1 has to block the entire V0 voltage. So, because in this circuit, if you take this particular circuit, in this particular circuit if this S2 is on, then this entire V0 is appearing across this S1 switch. So, the voltage rating of S1, you can say that Vs1 is nothing but V0. Generally, when you are selecting a particular switch, generally used to give a safety margin of 40 to 60%. So, you can select a device having 1.4 times of that V0. Let us say if you have V0 selected as 400 volt, then generally you will take Vs1 which is near to 650 to 700 volt, which is coming roughly to roughly 1.4 times of that V0. Generally people keep the safety margin going between 40% to 60%. So that one can choose the device going between 650 volt to 700 volt. Sometimes people have, I mean the designer have also selected 600 volt devices. That will also work. Obviously one has to make sure that while designing the PCBs for this converter, you must ensure that the voltage across these devices is not going beyond its specified rating. So the voltage rating of the S1 switch we have defined. Now another important thing which is needed is the RMS current. So the RMS current of S1 we need to calculate. Now before that, let us understand how we can calculate the RMS current from any power converter if it is if any generalized power converter is given. So let us take a very simple power converter defined by uh, a half bridge, which is one of the fundamental building block of any voltage source power converter. So we have, let's say we have VDC applying across this half bridge, and the output of half bridge will be having, we will assume we have a constant current which is been drawing from this half bridge. This is one of common architecture we find in voltage source converters, where the inductor is kept at the output or pole of the half bridge. For example, if it is a buck converter, the combination of L and C is kept at the pole of half bridge to smoothen the voltage and current which goes into the load. So the large inductor at the pole of the half bridge gives the characteristic of constant current being drawn from the half bridge. There will be ripple, but it is minimal. So it can be assumed that we are having a constant current which is being drawn from the half bridge. So we assume that we have the constant current, so I naught coming out of this half bridge, and let's define this as a SA switch and SB switch. So when SA is on, and that particular time we define that particular time, let's say DTS period. That means D is the duty ratio which defines the fraction of the time of the switching period TS. This is defined as switching period, or 1 by switching frequency, you can say 1 by F switching frequency for this is generalized voltage source converter, and this is nothing but a duty ratio, the fraction of time during which the SA switch is on. So when the SA switch is on, the current through SA switch is nothing but I naught, because that current is going through the load. You can say that going I mean is coming out of that particular half bridge. Similarly, when SA is off, so when SA is off, we can write that the current through SA is nothing but 0. So let us try to find what will be my RMS current, or what will be my RMS current rating of this SA switch. So we can write I RMS of SA is nothing but, we can write, so it is nothing but a root mean square. So root, we have to take mean. So since the SA is on for DTS period, and this SA is off when during this 1 minus DTS period, I mean the remaining portion of the period SA is off. So some portion of the period SA is on, and the remaining portion of the period SA is off. During that time my SB is on. So the current which is coming out of the half bridge is going through the SB. But here we are bothered about how we can calculate the RMS current of SA switch. So we have to take a mean. So what we have understood that for DTS period SA is on, for 1 minus DTS period SA is off, then again in the next cycle again for DTS period SA is on. So we have to take the mean that means we have to take the average, that means we have to take the average in one switching cycle. So we can write 1 by Ts, 0 to Ts, and the current through SA or ISA. So let me write this as ISA square times dt. Now we can write this particular expression as 1 by Ts. So from 0 to dTs, the SA takes I naught current, so this is I naught square plus dTs to 1 minus dTs, or you can say the remaining portion, you can just write Ts, it is nothing but 0, because during 1 minus dTs period it is 0, it is carrying 0, it is having 0 current, so it will be this one and dt. Now this will nothing but 1 by Ts, and that will I naught will come out, and that will be dt, integration of dt going from 0 to dTs, and that will nothing but gives you Is SA 1 by Ts I naught square. Since it is going to 0 to dTs, we will have the t which is going to 0 to dTs, nothing but 1 by Ts I naught square dTs. This Ts get cancelled, that will come out to be IRMS of SA is nothing but I naught coming out under root of D. That means if you have to calculate in any generic power converter what is the RMS current flowing through the switches, one need to know what is the fraction of time during which the particular device is on in a switching period. So here we have assumed that for D fraction of the switching period this device S1 is on, so we get the IRMS current going through the switch SA is nothing but I naught, which is the current which will be flowing through the switch SA when switch SA is on during DTS period. So that particular RMS current is nothing but I naught times under root D. So similarly the same concept we will use and calculate the RMS current of switch S1. So for that we have already assumed that our current at the input which is there, which will be flowing through this diode bridge rectifier, and this ID is nearly equal to Is in positive half cycle. In the negative half cycle the ID is nothing but equal to minus of Is which is there, and we have already assumed that because of the operation of this converter my Is of t is nothing but Is peak sin omega t. So we can say that in the positive half cycle my ID, or which is nothing but the IL, is nothing but Is peak sin omega t. Obviously I am neglecting the high frequency ripple which will be there over this average value of this IL current. So that particular thing is been neglected here. So we have assumed that this, or we have taken the approximation that my current which is flowing through this one is nothing but this in positive half cycle, and that current is the one which will be flowing through the S1 switch when it is on during DTS period. So we can very easily write that Is1 RMS is nothing but, the current which is going through the switch S1, the RMS value of that we can write that 1 by T by 2. Why we have taken 1 by T by 2? Because only in positive half cycle we have taken, because in negative half cycle it is this ID is nothing but minus of Is peak sin omega t, and this S1 will be seeing the same variation after the T by 2 period. So we have taken the average, we have to take the mean from 0 to T by 2 period is nothing but 1 by 1 T by 2 we can take, and we can write this one as going from 0 to T by 2 Is of t square we can do times d of t dt. Now what is d of t? We already know, because during d of t ts period only my S1 is on. So that's why as during t period S1 is on. So by using the same analogy as we have derived some time before, we are using the same thing and we can write in this particular manner. We can then put the values 2 by t 0 to t, can write is peak square sine square omega t dt was nothing but d of t is nothing but 1 minus modulus of Vs peak sine omega t divided by V naught times, or this particular thing is integrated over 0 to t by 2. Now using this expression, one can put this particular expression in high end mathematical software and can easily able to evaluate what will be your IS1 RMS, because if we see in this particular expression Vs peak, generally once you know what is the RMS input voltage, you know your Vs peak, which is nothing but root 2 times that RMS value. Once the converter is defined, the specification is defined, that means you already know what is your V naught value. So this particular two variables you know. Similarly, using the power imbalance method, you can easily calculate what is your IS peak which you expect it to be to have from the input side. So for example, if let us say if someone says that one need to design the power converter of 3.3 kilowatt. So let us say my PL value someone has given 3.3 kilowatt, that implies if we assume the efficiency to be 100%, we can say that our P input is nothing but 3.3 kilowatt, or you can take a efficiency 95% efficiency or 97% efficiency, which is a good estimate to calculate the P in, which is nothing but 3.3 kilowatt divided by efficiency number. So here let us take efficiency equal to 100%. So our P in will also be 3.3 kilowatt. That implies I can easily calculate this P in is nothing but Vs peak Is peak by 2 equal nothing to 3.3 kilowatt, and that will give you Is peak. Since mostly we know what will be my AC peak input voltage, so I can easily calculate using this formula. I can easily calculate my Is peak, which is again, if we generalize this formula, it is Is peak is nothing but PL times 2 divided by Vs peak. Now using this formula, one can also know what will be my Is peak, and thus one can easily calculate what will be the rating or what will be the RMS current rating of this S1 switch. So in this particular lecture, we have seen how we can calculate the capacitance value, how one can easily size the capacitance value once they know what will be my load power, as well as what will be my the output voltage to be kept, as well as what is the allowable voltage ripple, and your line frequency one already knows one, because this particular converter is going for certain for AC voltage I mean it has input which is nothing but AC voltage. So one easily know one must know what is the line frequency. So using that 3-4 quantities, one can easily calculate the capacitance value. And if we see that capacitance value has the second line harmonic frequency component, and because of that the size of capacitance is enormously high in case of any single phase AC to DC converter. Here we have explained the same concept using boost PFC converter, but it's same, this concept will remain be the same for different single phase AC to DC power converters. Obviously single phase AC to DC power converter having unity power factor current drawn, so that is also one important condition it is there. Then we have seen how we can size this switch S1. We have understood the voltage rating of S1 is nothing but equal to the V naught, which is output voltage, and then we have understood how one can obtain the expressions of RMS current flowing through the switch in any generic power converter, and using that concept we have also obtained the expression of RMS current for switch S1. Using this expression one can evaluate the RMS current ratings of the devices and can select the appropriate device. If one has to select the MOSFET, they can use the RMS ratings. If one has to select the IGBT, then one has to also evaluate the average current flowing through the switch S1, and that is depend nothing upon Vs peak, V naught value, Vs peak, which we already know, because we know to what voltage, AC voltage one will be connecting the converter, and what is the output DC voltage, and what is the peak current one can expect in a peak current which will be drawn from the AC voltage source, one can expect from the power converter if it is designed for certain power level. So, using that particular scenario one can easily calculate what will be the value of IS peak, and thus one can put this particular expression in any high end computing software and can calculate the RMS current which will be flowing to the IS1. In the next lecture we will see how we can calculate the RMS current going through the IS2 switch, and we will also see the ratings of this diodes, and then we can further move ahead and see how we can do the closed loop control of this power converter. Thank you for patiently listening to this lecture.